Hello everyone. So today we're going to find T sub A, the matrix that represents the reflection across the line y equals 2x with respect to the standard basis of R2. Okay, so essentially what we're looking for is a matrix that represents the transformation. And what you can do is, instead of you having to compute something somewhat tediously here, you can go ahead and work with this transformation matrix to compute images of vectors. So basically the idea is like, if I give you a vector, what this matrix will do is when you multiply this vector by this matrix, it gives you the image when you reflect through the line, across the line y equals 2x, excuse me. So first of all, let me go over what the standard bases are here, or the standard basis is, my apologies, which is in R2, it's 1, 0, 0, 1. It's these two vectors. And what you're looking for is this right here, T sub A, which is consisting of the image of 1, 0 under this transformation, so the reflection of 1, 0 across the line y equals 2x, and the reflection of 0, 1 across the line y equals 2x. So that's what T of 0, 1 mean and T of 1, 0 mean. Okay, now here's let me draw some geometry here. So we've got the line y equals 2x, which looks like that. And what I'm asking here is, if I take the vector 1, 0 here, if I reflect it across this line, what's my image going to look like? So when you're reflecting something across the line, the end here, the end of my vector here, my head, put it that way, and the head of whatever the image is, those 2 points are connected by this line, which is perpendicular to the line. And that's something about geometry. That's what a reflection, if you look at the definition of reflection, we have that property. Now we can compute that reflection of 1, 0 across the line y equals 2. It is doable. However, it can be tedious in my opinion. So I'd rather use something else. And why the point of this video is to use like all our tools that we have from linear algebra here to work with to find these transformations. Do this a little easier, put it that way. And here's how this works. So I have two images of two vectors here. I have T of 1, 2, which is 1, 2, and the idea behind that is as follows. If you take the vector 1, 2, and you reflect it across the line y equals 2x, it's going to be on the line again. Yeah, the vector 1, 2 is on the line itself. Yeah, when x is 1, y is 2, put it that way. Well, that's on the line. So when you reflect something that's on a line, across a line, it's still on the line. So we have 1, 2. And then I have the vector negative 2, 1. And if you reflect that vector, just put this in blue, across the line y equals 2x, it becomes 2, negative 1. So I picked that vector for a couple reasons. Because it's easy to see the reflection. The vector minus 2, 1 is already perpendicular to 1, 2. So when you reflect it, it becomes basically just switch the signs. So it's just kind of like, think of it this way. It's like, since the blue is perpendicular to the green, when you reflect it, it just flips over, like, and then you switch the places here. Well, anyways, the special thing about the 1, 2 and negative 2, 1 here, besides the fact that we can find the images, negative 2, 1 and 1, 2 make an orthogonal basis, basically. Here, it's two orthogonal vectors that are a basis for R2. So what's so special about that? Well, if you recall, so going back to learning the course, and let me write this out, that minus 2, 1 and 1, 2 is our orthogonal basis. The special thing, first of all, first thing that's great is that because this is a basis, you can write every vector in R2 as a linear combination. So for example, 1, 0 can be written as a combination of 1, 2 and negative 2, 1. And likewise 0, 1, same thing. So what's so great about this? Well, because a transformation, a linear transformation, as the name denotes, is linear, that means if you take the transformation of 1, 0, it's equal to taking the transformation of 1, 2 times a constant plus that same constant, another constant, C2 times the transformation of minus 2, 1. So again, if you know a vector is a sum equals the sum of two vectors, then the transformation of that vector is equal to the sum of the transformations of the vectors in so many words. That's what we're working with linearity here. And the same thing happens with t of 0, 1 equals d1 t of 1, 2 plus d2 t of minus 2, 1. And the whole idea here is that we're using is that we know the images of 1, 2, and minus 2, 1. So we can basically find any image of any vector based on the fact that we know the images of those transformations. Okay, so, but the question here is, that's great, but how do I find these constants? I need to find C1, C2, D1, D2, okay? And well, here's what we're gonna look at next. If you have an I say an orthonormal basis, but it should be orthogonal here. Let me change that. If you have an orthogonal basis, but the word orthonormal would work out as here. If you have an orthogonal basis of E, then if you write a vector as a linear combination of the basis vectors, the way you get each of the constants in front that forms a combination is by taking the dot product, in this case, or an inner product of each of the individual basis vectors with the vector you're trying to write as a combination. So what I'm trying to get is this. If we go back to 1, 0 equals C1, 1, 2 plus C2 minus 2, 1 right here. The way you get your first constant is when you take the vector 1, 0 and you dot it with 1, 2 and take the magnitude of that squared. And that would give you 1/5. And if you want to get C2, you will take now 1, 0 and dot it with negative 2, 1 over its magnitude, and you get negative 2/5. And likewise for D1 and D2, you're going to work with the vector 0, 1, you're going to dot it with 1, 2 divided by its magnitude squared, and similarly for D2. And essentially what we find out is that 1, 0 equals 1/5 times 1, 2, minus 2/5 times minus 2, 1. And likewise 0, 1 equals 2/5 times 1, 2 plus 1/5 times the vector minus 2, 1. And if you take the image of t of 1, 0, linear transformation, it's going to equal 1/5 the transformation of 1, 2 minus 2/5 the transformation of minus 2, 1. And these were the transformations here. And if you do some algebra and add things up, this is your image of t of 1, 0. And maybe you want to pause this for a second, but the transformation of 0, 1 is very similar, and you get 4/5, 3/5. And right there is when you combine the two results, the negative 3/5 and 4/5 times 4/5, 3/5, that right there is your matrix that represents the linear transformation. So basically here, if I wanted to figure out what the transformation of the vector let's say 4, 3 was, all I need to do is multiply this matrix by the vector 4, 3, and it'll tell you what you would have as your answer here. Okay, and if we did that, let's see, sorry, that looks like a division, that's just 4, 3 here. Minus 12/5 plus 12/5, actually that's 0, that's nice. And then you would get 16/5 plus 9/5, which is 25/5, you get 5. So the vector 4, 3 reflects, and you get 0, 5 when you're reflected across the line y equals 2x. Okay, no, it's not bad. And yeah, and basically that's all you need to do. To find any image of any vector, all you need to do is multiply it by this matrix. So it's really nice to have here as a tool. Okay. And there's other ways of figuring out those constants, the C1, C2, D1, D2. You could use a transition matrix from one basis to another. That's another thing we could have done. And I think I have a video on that subject, so I would look that up. But yeah, but basically I wanted to go over this problem. It's not so much a problem where you have to, it's like touches on something so critical, but it touches on a lot of the tools that you've used in this class. Okay, well, I hope you found this interesting. Thank you for your time.